Okay, this video is going to combine the electric field and electric potential, and we're going to look at something called electrostatic shielding. So, we looked at work. Work is the negative your change in energy, which is negative Q change in V. Okay, final minus initial. So what does this tell us? It tells us that it takes work to move a charge from one potential energy to another. And no net work is required to move a charge between 2 points. So if your potential is different, if your electric potential is different, it takes work. If it's the same, then this would be 0, so work would be 0. Now, potential difference. Alright, we talked about electric potential. Potential difference is like what a battery has. Okay? Potential difference is the change in potential between 2 points. A measure of the electric change or work required to move a charge independent of the charge value. Okay, so a measure of energy. Oh, wrong color. Black won't really do any good. Okay. A measure of energy change or work required to move a charge. The units for potential difference is V, same as volts. So basically, potential difference is the change, while electric potential is just the actual value. Okay, so we're just adding that triangle in front of everything. Now there's this thing called equipotential lines. Now if we break it down, it makes a lot of sense. Equa, equal, potential. So we're drawing lines where the potential is equal. Equipotential lines are always perpendicular to the surface. And they're kind of similar to contour lines on a map. So these are the field lines, right? So we have electric field coming out, coming out, coming out. And let's say right here, this electric field is 4. I'm just picking a random number. Then right here is 4. And right here is 4. And right here is 4. Okay. And everywhere along this line, it's 4. Okay. So we're saying the electric field anywhere around here is going to be 4. Now, electrostatic equilibrium. It means no net motion of charge in a conductor. Charges are always moving. Things would only stop moving if we had absolute zero. If we reached absolute zero, 0 Kelvin, then things would stop moving. But if we're not there, then there is always some movement. You know, you've got a sphere or metal, a conductor, whatever it is, and the electrons are all moving around inside of it, having their good old time. But when it's in electrostatic equilibrium, there's no net movement. So overall, one might be moving left, one might be moving right, but it all kind of cancels out. Okay, so there's not some overall direction of movement of the charge. An isolated conductor in electrostatic equilibrium. E equals 0 everywhere inside. Okay, these are things to remember about electrostatic equilibrium. So, E is 0 inside. This makes sense because I told you that there is no single direction that everything's moving in. Nothing is pushing it. If there's no net movement, then there's no net force. Newton's first law. And since E equals F over Q, if there's no net movement, no net force, no net electric field. Kind of cool. So if you have a conductor inside of it, you have an electric field of 0. All excess charges are on the surface. So if it's a positively charged or negatively charged, the excess charges, the extra charges, will all be located on the surface of an object, which makes perfect sense. Coulomb's law. You know, like charges repel. They're going to repel to be as far away from each other as possible, which is the surface. The electric field outside of a conductor is perpendicular, which makes complete sense as well. All the charges are pushed to the surface, right? So if, let's say, we had an electric field right here that wasn't perpendicular to the surface, well then E equals F over Q. There would be some force on those charges pushing them that way, creating motion. But there isn't. So all your electric fields are perpendicular to the surface, pushing everything to the surface, but not like down the conductor, something like current. Alright, an electric potential is the same everywhere within a conductor. This also makes sense. Inside, your electric field is 0. Therefore, your force is 0, and your work is 0. Work equals F times D. If F is 0, work is 0. The surface, E, is perpendicular. Therefore, the charge doesn't move through an electric field, so it doesn't move any distance. Okay, so there's no distance movement along that surface. So your work equals 0. Right? Distance is 0, work is 0. Electric potential is related to work. So if your electric potential, if your work is 0, then your electric potential will be the same, because back here we have change in energy equals work. So your potential difference, your change in potential, is, if your work is 0, then your change in potential is 0. Okay? Go back to look there. Now let's look at an example. 2 electrons are independent of external influences, which means, yes, other things exist in the world, and yes, we're going to ignore them. They are moved 1 centimeter apart to 1 nanometer apart. So they moved from 1 times 10 to the negative 2 meters to 1 times 10 to the negative 9th meters. So they're moved closer together. How much work is done? What is the change in potential? So we're looking for change in electric potential felt by one of the electrons. Now there are 2 electrons, so we know Q1 and Q2 are 1.6 times 10 to the negative 19th. Okay, so 1.6 times 10 to the negative 19th, and I grabbed and I brought this up. Now we're looking for work. We have our energy. Work is change in energy. So we would find change in UE equals K Q1 Q2 over change in R squared. Okay? So we're looking for the change on this side, and the only thing that changes on this side is R. So that's where our change goes. So change in U. So we have K, 9 times 10, K times 1.6 times 10 to the negative 19th squared. Hold on. I made a mistake when I wrote this out. You got to be careful when you do these changes. It is the change of r squared, not change of r squared. It actually does make a difference. The math works out a little bit differently. Divided by our final, which is 1 times 10 to the negative 9th squared minus our initial, 1 times 10 to the negative 2 squared. Okay? Make sure you put the squares that way, because if you do, 1 times 10 to the negative 9th minus 1 times 10 to the negative 2 squared, that's a different number. Don't do that. You work it out and you'll find your work. You get negative 2.3 times 10 to the negative 24th equals your change in energy. Now work equals negative change in U, so work is positive 2.3 times 10 to the negative 24th. And to find the electric potential felt by one, you would need, go back. The electric potential is U divided by Q, which is KQ over R. So V equals KQ over R. I'm not going to work it out. Q is 1.6 times 10 to the negative 19th. R is 1 nanometer. And you can find V. Alright, that's it for the lesson. Good luck on your homework.